So, good evening. Thanks for joining in this webinar session. And this is Saravana Krishnan from CIKIT Electricals and Technologies. And in this webinar, we will be explaining about the risk designing of lighting protection system as per the standard 62305 part 3. So, in our earlier webinar, we have explained about the risk assessment calculations. And as a continuation of the risk assessment calculation, we will be explaining about the designing methodologies in this webinar. So before entering into this webinar, just a small brief introduction about our company. CIKIT was incorporated in 2018. So even though it is a 4 years old company, we are having an experience of more than 17 years in this field of lightning protection and earthing. And our specialization is we are providing end-to-end solutions starting from the site survey, risk assessment calculations, performing designing, material supply, installations, and performing maintenance and auditing of the existing systems. And we are providing customized solutions as per the site requirements. We are not following the only one standard for all the site conditions. Based on the site conditions, we will be referring different standards and we will be providing the customized solution for each site conditions. So these are the different standards which we refer for different site conditions. So if we take this renewable energy, we will be following NBC 2016 along with this standard IEC 62305. So the NBC has explained about this shadow analysis. That is, if the height of the air terminal is above 500 mm, the shadow will fall on the panel and it will have an impact on the power generation. So that restrictions on the height of the air terminal was provided by this NBC 2016. And for high-rise building, apart from the lightning directly striking on the building, on the top of the building, the lightning may strike at the middle portion of the buildings as well. So we have to consider some special considerations while designing lightning protection system for buildings above 60 meters. So that were explained in detail in NBC 2016. And for oil industry safety directorate has published a set of rules to be followed for designing this lightning protection system for oil sites, because the risk due to lightning on those conditions will be very much higher. Apart from this physical damage, the lightning may result in explosion as well. So in oil industry, we have to follow OISP GDL 180. So these are some of the standards which we follow for different site conditions. So lightning. So generally people will think that lightning is nothing but discharge happening from the charged cloud to the ground. So but that is not the case. So discharge happening from the cloud to the ground is only one type of lightning. So that is called as cloud to ground lightning. There are two more types of that. One is discharge happening within the same cloud. So the positive charges will be on the top portion of the cloud and negative charges will be on the bottom portion of the cloud. So if the discharge happening within the same cloud, it is called as intra-cloud lightning. Similarly, if the discharge happens from one cloud to another cloud, so this type of lightning is called as cloud to cloud lightning. So in general, if you take the quantity of lightning, the number of inter-cloud and intra-cloud lightning will be very much higher than the cloud to ground lightning. But we are considering protection for this cloud to ground lightning alone, because that lightning alone causes damage to these physical structures and causes injuries to human beings and results in failure of electronic equipments and all. So we will be considering only the cloud to ground lightning, but the number of lightning strikes due to this intra-cloud and inter-cloud will be much higher than the cloud to ground lightning. So during thunderstorm conditions, because of the charge built up in the cloud, the opposite charges will get induced on all the objects connected to the ground. So in this example, if you see, there are only two structures are there. Only one tree is there, remaining is ground. So if there is any other building, then this building also will be sending this positive charges. If any person is standing, means that person will also be sending the positive charges. But the lightning path will be closed through the positive charge which reaches the negative charges first. So in our case, the positive charges from the tree is reaching this negative charges before the positive charges from the cloud reaches it. So the path is closed through the trees. If there are any other higher structures nearby the tree, means the lightning may choose the path through the building. So it is not that only the tallest structure will be sending positive charges. all the bodies that is connected to the ground will be sending the positive charges, and the path will be closed through the positive charge which reaches the negative charges first. So before providing solution, we need to identify the root cause for the particular issue. So in our case, the issue is damage to the living organisms and physical structures and failure of electronic equipments. So before providing solution, we need to identify what is the source which causes it. So if you take the lightning directly striking on a building and causing the damage will be considered as direct effects of lightning strikes. But apart from the direct effects of lightning strikes, lightning may strike at some other place and may cause damage in our house or building. So this is called as indirect effects of lightning strikes. So if you take this lightning striking on a power line, in this case the lightning is actually striking on the power line. Because of this lightning strike, the surges will travel through the power line and it enter into a house, and it will result in failure of electronic equipments inside the house. So here the lightning is striking at some other place, but the damage is faced at some other place. So this is called as indirect effect of lightning strikes. So if you take this indirect effects, the indirect effect will be very much severe in hospitals and in places where the explosives are stored. So for example, if you take hospital as an example, the failure of electronic equipments will result in loss of human life. So that is very severe. At the same time, if you take some structures where we are storing some explosive materials, so in that case, if there are any sparks due to the failure of electronic equipments, because of the sparks, it may result in huge explosion. So the indirect effect is also very much severe according to the site on which we have facing. So first thing is we need to identify the source which is causing this damages. So there are 4 sources that can cause damage. The first source is lightning directly striking on the structure, and second one is lightning striking near the structure, and third one is lightning striking the power line, and fourth one is lightning striking near the power line. So these are the 4 sources that can cause the damages. So first thing is we need to identify the source that caused the damage, and after that we need to go for the solution part. So we have explained about the 4 sources that cause damage, and the damages can be classified into 3 types as injury to human beings, physical damage, and failure of electronic equipments. So the corresponding losses and risks we have explained in detail in the previous webinar, and we have shared the link in chat box also. So you can refer that video link for knowing about the how can we reduce the risk due to lightning, and what are the preventive measures that can be adopted for reducing the risk due to the lightning. So if we are going for this lightning protection system design, so there are various processes involved in this complete designing. So the first one is proper site analysis. So we cannot provide a generalized solution. So for each and every site, we have to perform the analysis, and we have to collect details regarding the site, like what is the location of the site, what will be the number of lightning strikes on that particular location, whether the building has any explosive materials, so what is the risk of fire and explosion in the site. So like this, we have to analyze the site properly, and based on the site analysis, we have to perform the risk assessment calculations. So the risk assessment calculation provides 2 outputs. So the first output is whether LPS is required or not. So that is the first output of this risk assessment calculations. So, and the second output is what is the suitable level of protection. So for one side, whether I have to go for level 1 protection or level 2 protection, like that, what is the suitable level of protection for that particular site. So that will be the output of the risk assessment calculations. Based on the output only, we have to perform the designing. And based on the design, we have to supply the material, and there has to be a proper coordination between the material supply and installation. And the most important part in lighting protection system is the periodical inspection. So many people will install the lighting protection system and they won't do the proper maintenance and all. All these components are installed outside the building and they are more prone to corrosion. So we have to perform periodical inspection to ensure the proper working condition of those components. So periodical inspection is very much important in case of lighting protection system. So 6235 is the standard which we follow for performing this risk assessment and designing of lighting protection system. So in this webinar, we will be concentrating only on this 6235 part 3, that is protection measures for this lighting protection system. So it is mainly about this external lighting protection system, and in part 4 we will be explaining about this internal lighting protection, which is the protection for electronic equipments inside the building. So in this webinar we will be explaining mainly about this 6305 part 3. So if you take this complete lighting protection system, which it has two parts. So one part is external lighting protection system, which will provide protection to the buildings and structures alone. So that protection can be ensured by three components. The first component is air terminal, and second component is down conductor, and third component is earthing. So these three components will combine together and provide protection to the building. So if any lightning strikes, then the combination of these three components will provide a bypass, that is, it provides a shortest path to the ground for dissipating this energy. So here it protects the buildings from the direct effects, but all the electronic equipments inside the building are not protected because of this external lighting protection system. Because for these equipments, we are taking power supply from the outside. So if lightning strikes on this power line or data line, then the surges will enter into the building and it will result in the failure of electronic components. So in order to ensure complete protection, we have to provide surge protection devices. So the complete protection is the combination of external lighting protection system and internal lighting protection system. So the external lighting protection system provides protection to the buildings, and internal lighting protection system provides protection to the electrical and electronical equipments inside the building. So the combination of internal and external lighting protection system will provide the complete lighting protection system for the buildings and structures. So in this webinar, we will be concentrating only on this external lighting protection system. So as I mentioned, the external lighting protection system consists of mainly three components. So the first component is the air terminal. So air terminal is the component which intercepts the lightning. So if any lightning is coming, means this will be the part which receives the lightning. So that will be the first point of contact. So after that, the down conductor system acts as a bridge between the air terminal and the earthing system. So it provides shortest and a low resistance path to the ground. So it simply acts as a bypass, thereby protecting the building. And the earthing dissipates the energy received into the ground. So these three are the main components of the lightning protection system. So apart from that, there are two more components are there. One is lightning event counter, another one is testing. So the purpose of lightning event counter is it just registers the number of lightning impulses captured by this air terminal system. And the test link, it is just a disconnecting link. The purpose of test link is to inspect the earth pits and to check the continuity between the down conductors and all. So it is normally used for inspection purpose. The lightning event counter and test links are optional items, whereas air terminal, down conductor and earthing are the main components of the lightning protection system. So the 62305 part 3 has explained about three different methodologies for placing the air terminals. So simply placing a rod at the top of the building and connecting to the ground cannot be considered as a proper lightning protection system. So we have to determine the number of lightning air terminals required for that particular building and the position of each lighting protection air terminal systems. So for example, if you consider one building for which 4 air terminals are required, then I cannot place the 4 air terminals randomly. I have to place the air terminals at the suitable places to ensure the protection. So to determine the number of air terminals required for the site and the position of each air terminals, the standard has provided 3 methods. So the first method is protection angle method, and second method is mesh method, and third method is rolling spear method. So the protection angle method is the conventional method, And in mesh method, we will be simply laying the conductor in the form of mesh. And in rolling sphere method, we will be rolling an imaginary sphere. And this rolling sphere method is nowadays commonly used for designing this lighting protection system because of the limitations in the other two methods. So in the upcoming slides, we will be explaining in detail about the how to calculate the protection provided by air terminals among these different methods. So this one is the protection angle method. So from the name itself, we can observe that protection angle method. So in this method, the protection mainly depends upon the angle. So the angle depends upon the height of the air terminal. So in this, if you observe means the protection angle alpha 1 and alpha 2 are different, because for alpha 2 the reference plane is the terrace level, but whereas for alpha 1 the reference plane is ground level. So if you consider the alpha 1, the height will be much higher, so the alpha angle is varying, depends upon the height. If you take this alpha 2, the reference is from the terrace level, so the angle is different. So in the protection angle method, the protection mainly depends upon the height of the air terminal. For depending upon the height, the angle of protection will be differ. So depending upon this angle, the radius will be varying. So since the protection is mainly depending upon this angle, this method is called as protection angle method. So the standard has provided a graph for calculating this radius of protection for different heights. So this is the graph provided by the standard 62305 part 3. So in this, we can find the angle for each heights. So for example, if you take this, if I extend a line at 2 meter height, so for 2 meters, the angle is around 70 degrees for level 1 protection. So for level 2, it will be around 73 or 74. So similarly, if I extend this line, I can find this angle for different level of protection. So if I consider this level 1 protection, then the angle is 70 degrees. So it is nothing but like a right angle triangle. So in this right angle triangle, the height I am taking is 2 meters. So this side, the height is 2 meters. And for this 2 meter, the angle is 70 degrees. So I know this angle and I know the height. So from this trigonometrical functions, we can calculate the radius of protection or value. So we know that tan theta, tan angle is equal to opposite side by adjacent side. So in our case, the opposite side is R and the angle is tan 70 degrees. So tan 70 degrees is equal to R divided by 2. So in this, if we substitute the values, we can find that R is equal to 2 into tan of 70 degrees. So the tan 70 will be approximately 2.8. So for 2 meter height at level 1, the radius will be approximately 5.6 meters. Because tan 70 will be approximately 2.747. So if you round it, means it will be coming under 2.8. So 2 into 2.8 will be 5.6. So that will be the radius of protection for an air terminal of height 2 meters at level 1. So similarly, we can calculate the radius of protection at different heights for different levels. So this is the calculation behind this radius of protection calculation for protection angle method. So we have performed this calculation for different heights at different levels. So in this table, we can find that for the height of 2 meters. So for level 1, the radius angle will be 70 degrees and the radius will be 5.6. So we have shown the sample calculation in the previous slide. So using this angle, we have to calculate the radius, corresponding radius for the particular height at different levels. So everything is depending upon the angle value. So this method is called as protection angle method, and the limitation of this method is it will be very difficult to perform the designing for complex structures. So earlier the buildings will be in the shape of either square or rectangle, but nowadays the buildings shapes are very complex to explain. So this method will be very difficult to perform the designing for complex structures. And one more thing is the graph is provided up to 60-meter height. If the building height is more than 60 meters, then we cannot go for this protection angle method. So these are the limitations of this method. So to overcome that, we will be going for this rolling spear method. So the second method is mesh method. So in mesh method, we will be simply laying the conductor in the form of mesh over the structure to be protected. Earlier, this method was commonly used in industries where they have used metallic roof sheets. But nowadays, because of this rooftop solar, we are not preferring this method because the height of the solar panels will be higher than this conductor laid on this metallic structures. So the solar panels will not be protected by this mesh conductors which are installed earlier. So nowadays this method is not commonly used by many people because of this installation of rooftop solar panels. And in this method, the size of this mesh depends upon the level of protection. If I am going for level 1, then the size will be 5 cross 5. So 5 cross 5 in the sense this side the length will be 5 and width will be 5. So this will be 5, this will be 5. So if I am going for level 2, then the mesh size will be 10 by 10. So if I am going for level 3, then this side will be 15 by 15. So if I am going for level 4, the mesh size will be 20 by 20. So based on the level of protection, I will be increasing the mesh size alone. But this method is nowadays not commonly used. So rolling spear method. So this is the method which we are commonly using for designing this lightning protection system. So here we will be rolling an imaginary spear over the structure to be protected. So for example, if you take this image, we are protecting this house from the lightning. So we will be rolling an imaginary spear, and the radius of the spear depends upon the level of protection. So for example, if you take level 4, we will be rolling an giant spear of radius 60 meter. So the radius of the spear itself will be 60 meter. If you consider the diameter, it will be 120 meters. So such a giant imaginary spear will be rolled over the structure to be protected. And we should ensure that the spear is not making contact with any parts of the building. So the spear can make contact only with the ground and the air terminals. So the spear should not make contact with any parts of the building. So if the spear makes contact with any part means, then the particular part will be considered as unprotected. So in this image we can observe that the spear is not making contact with any part of the images. Then in this case the structure can be considered as protected. So if it is making contact, then we have to place the air terminals accordingly to avoid the contact. So we cannot roll the imaginary spear over all the structures for ensuring the protection. So the standard has provided the formula for performing this calculations. So we need to ensure that the spear should not make contact with this structure alone. So if we increase the distance between the air terminals, then at one particular point, the spear will be making contact with the structures. So if you take any two air terminals, and if a spear is placed over it, then definitely some portion of the spear will be coming below the level of this air terminals. So if you consider this is the level of air terminal, then some portion will be coming below. So the portion of this sphere which is coming below, that will be considered as the penetration distance P. So if I increase this distance further, then at one point, what happens means, at one point this sphere will be making contact with the structure to be protected. So if I increase this distance between this air terminals, the level will be reducing, and at one point the sphere will be touching the structure. So if the sphere touches the structure, then that particular point will be considered as unprotected. So I have to find the suitable distance so that this contact of the sphere with this structure can be avoided. So this is the formula for calculating that. So the distance formula is 2 into square root of 2pr minus p square, where p is the penetration distance. So So the penetration distance is up to which portion the sphere is coming below the level of air terminals. So if there are any structures, then I cannot keep this portion up to this point. So if this structure is this object is not there, then I can increase the distance so that this portion of sphere can come up to this point. So if there are any objects, I have to consider the object as well, and the sphere should not make contact with the objects also. So the P is the penetration distance and D is the distance between this air terminals, and R is the radius. So the radius depends upon the level of protection. So based on this formula, I can calculate the maximum distance between the two air terminals. So we have to note one point here. So here we are calculating the maximum distance between two air terminals, and we are not calculating the radius of protection provided by one air terminal. In protection angle method, we will be calculating the radius of protection of only one air terminal, but in rolling sphere method, we will be calculating the area protected by the two air terminals. So what can be the maximum distance between the two air terminals? So that is what we are calculating here. So in rolling sphere method, we won't calculate the radius of protection provided by the one air terminal. So this is a calculation which we done for different heights for 0.5 meter, 1 meter and 1.5 meter. So as I mentioned, in NBC they have mentioned a factor called shadow effect for this solar panel. So I cannot increase the height above 0.5 meter. So in that case, if I consider the height of air terminal at 0.5 meter, then the maximum distance between the two air terminals can be 15.46. So which is I cannot increase up above 15 meters. It should be always less than 15 meters. So here the 15 meters is the distance between the two air terminals, and it is not the radius of protection provided by one air terminal. So here we always consider the distance between the two air terminals only. So similarly, if I consider 1.5 meter height, the maximum distance between two air terminals can be up to 26 meters. So using the formula, we can calculate the distance between the two air terminals for different heights and different levels. So I can calculate for 2 meters, 3 meters and 5 meters as well. So this is just an example. So in this, we can find that the distance between the two air terminals depends upon the level of protection and the penetration distance. So or penetration distance or height of the air terminal. So these are the two factors which determines the maximum distance between the two air terminals. So if you take normal buildings, the probability of site flashing will be very much lower. But if you consider a building of height greater than 60 meters, then the probability of lightning striking on the side of the building than the top portion of the building will be much higher. So the lightning striking on the side of the building is called as site flashing. So if the height is greater than 60 meters, then the probability of site flashing will be higher. So this event was recorded during April 24, 2022. So the lightning has struck on the middle portion of the building rather than striking at the top portion of the building. So the risk due to lightning on high-rise building will be very much higher. So the standard has provided a set of rules to be followed for high-rise buildings. So if the building height is greater than 60 meters, then I have to provide additional rings on the vertical side of the building for the top 20% of the building. So this is the reference provided by the standard 62305 part 3. NBC 2016 has provided much more clear picture for this, and this is the reference from NBC 2016. So here we can find that if the building is more than 60 meters, for example, if you take 100 meters as an example, then up to 60 meters there is no protection required. After 60 meters, then at 60 meters we have to provide one external ring for taking care of the side flashing. And after 60 meters, I have to provide a ring at every 20 meter difference. So I have to provide an external ring at every 20 meters above 60 meters of height to protect the building from the side flashing. So this is a reference provided by the NBC standard. So if the building height is less than 60 meters, then the damages due to the side flashing will be much lower. So there is no need for providing this additional vertical rings. But if the building height is more than 60 meters, we have to consider this side flashing as well. So we are planning to conduct a separate webinar series related to this risk associated with this high-rise building on due to this lightning strike. So we will explain this calculation in detail during that webinar. So this is just an outline. So if the building height is more than 60 meters, we have to provide additional rings on the vertical to protect the building from the side flashings. So the next part is a down conductor system. So the purpose of air terminal is to intercept the lightnings, and the purpose of down conductor is to carry the energy from the air terminal to the earthing system. So it simply acts as a bypass to the building. So it simply diverts the energy from the air terminal to the ground without damaging the structure. So we have to provide down conductors at equal intervals to ensure that the energy is dissipated to the ground as soon as possible. So the down conductors provided should be the shortest path to the ground. At the same time, the number of joints and number of bends in the down conductor should be as low as possible. The distance between the two down conductors recommended by the standard is, for level 1 it has to be 10 meters. So which means that I have to take one down conductor at every 10 meters intervals. At level 4 the distance between two down conductors can be 20 meters, which means that I have to take one down conductors at every 20-meter intervals. So for example, if you consider a building of 50 by 50, it is not sufficient to take the down conductor at the 4 corners of the building alone. So depending upon the length and width, I have to take one down conductor at every 20 meters. And the down conductor sizing should be greater than 50 square mm. So the minimum size of the down conductor can be 50 square mm. We cannot reduce the down conductor further. So that is the minimum dimension provided by the standard. And the standard has provided recommendations for different materials that can be used for like air termination system, down conductor system and earthing system. So these are the different materials that are recommended by the standard. So the standard does not recommend only one material. So it has recommended copper, hard GI, stainless steel and copper coated steel, aluminium and all. And in aluminium they have clearly mentioned that the aluminium is not suitable for grounding applications. So the corrosion rate of aluminium will be very much higher. So aluminium is a very good conductor. We are using this aluminium as the transmission lines and all. So it has a very good conductivity. But the problem with aluminium is it corrodes very much faster in the soil conditions. So aluminium is not recommended to use below the ground levels. At the same time, there is one more term called galvanic corrosion. So apart from this corrosion due to the environment, if we interconnect two dissimilar materials, so because of the connection between two dissimilar materials, the one material will be acting as anode and another material will be acting as the cathode. So the corrosion will happen if we interconnect two dissimilar materials. So the aluminium should not be connected with this copper. So this corrosion is called as galvanic corrosion. So the aluminium should not be directly connected with this copper. Sorry. And hot dip steel also, it is not recommended to connect a hot dip steel directly with this copper. So in this applications, so we have to use bimetallic connectors for making contact with the different materials. And if you take this copper as an example, the copper can be used in solid form or standard form. In solid form itself, it can be used in strip form or as well as the rod form as well. So these are the different materials recommended by the standard for the LPS components. So in this table they have explained about this minimum cross sectional area for using it as a air terminal and down conductor. Sorry. So if you take this copper, so the copper can be used in solid tape form. So the tape form will be normally which we use is 25 by 3 strips. Or it can be used in the round form. So round form is a rod. So for rod and all, they have maintained as a 50 square mm was a minimum cross section area. So if you consider the cross section area of rod, the cross section area formula is pi r squared. So pi r squared is 50. So r squared will be 50 by pi. It implies r is equal to square root of 50 by pi. So if you calculate this, the radius will be around 4 mm and the diameter of the rod D will be 8 mm. So we can use, if we are using a rod as the form of down conductor, means the diameter of the rod should be 8 mm. And here, so they have mentioned the 176 mm. So they have mentioned C as the superscript. So which is for this air terminal. So if I am using an air terminal, the cross section area of the air terminal should be 176 square mm. So if we are taking this down conductor for one air terminals, we need to provide minimum of 2 down conductors if I am providing only one air terminal. And we need to ensure that at every air terminal there is a 2 parallel paths for the lightning impulse current to go. So if any lightning is striking on air terminal, at the base we need to ensure that 2 paths or parallel paths are provided. So if any lightning impulse current is traveling through the rod, it will be having two different paths. So the lightning energy, if current I is coming, means it will be distributed into 2 parts, I by 2 or I by 2, for example. So in this case, the current flowing through the down conductor will be lower than the current which will be intercepted by this air terminal. So the cross sectional area of this air terminal will be always higher than the cross sectional area of the down conductors. So for down conductors we will be considering 50 square mm, but for air terminals we will be considering 176 square mm, because the current flowing through this air terminal will be higher than the current which will be flowing through the down conductor. So we always consider higher size for this air terminal than the down conductor. And for aluminum also, the minimum cross-sectional area for this down conductor is 50 square mm. And the copper coated steel, aluminum alloy can be used, hard dip galvanized steel can be used, copper coated steel can be used. So the standard does not stick to only one material. They have provided recommendations for different materials in different forms. So they have not recommended one material in one configuration alone. For each material they have provided different configurations, and for each configuration they have mentioned the minimum cross-sectional areas. So these are the materials that can be used and in different configurations for this air termination and the down conductor system. In this material, the aluminum should not be used below the ground level. So aluminum is not recommended for these earthing applications. So earthing system. So till now we have explained about the 2 main components. One is air termination system and the down conductor system. So the earthing system is responsible for dissipating this energy into the ground. So the standard has explained about 2 different methodologies. So first method is type A arrangement and second one is type B arrangement. So in type A arrangement we will be providing vertical earth electrodes, and in type B arrangement we will be providing a ring surrounding the building alone. So there won't be any vertical earth electrodes in this type B arrangement. In type A arrangement we will be providing only one vertical earth electrode for each and every down conductor. If we are going for type A arrangement, and the number of earth electrodes for one lighting production system should be minimum of 2 numbers. In any case, the number of earth electrodes should not be less than 2 numbers. And type B arrangement is commonly used for areas with high resistivity, where the standard clearly mentions that if the soil resistivity is more than 3000 ohm meters, it is always recommendable to go for this type B arrangement, because in type B arrangement we are forming a grid like structure, that is a ring surrounding the building. So the area of contact with this soil will be very much higher, so the dissipation will be good in type B arrangement. So the conductor should be laid at a distance of minimum 1 meter from the structure, and the depth should be minimum of 500 mm. So the depth should be minimum 500 mm below the ground level. So these are the 2 different arrangements provided by this standard for the earthing configurations. So these are the materials recommended by the standard for this earth termination system. So in this we can observe that they have not provided details of the aluminum. So aluminum is not recommended for use below the ground level. So the first one is copper. In all the materials they have provided different dimensions for earth rod, earth conductor and earth plate. So if I am going for plate, then it can be 500 by 500. If it is lattice plate, then it has to be 600 by 600. So if we are going for rod, so the commonly used configuration in rod is hard dip galvanized and copper coated steel. So if we are going for hard dip galvanized or copper coated steel, we can use 14 mm dia rods. So the dimension, that is minimum the rod dimension should be 14 mm. And if I am going for pipe, hot galvanized pipe, the diameter of the pipe should be minimum of 25 mm. So this is the standard. This is the specification provided by 62305 part 3, and they have not provided details about this aluminium because aluminium is not recommended to use below the ground levels. So 62305 clearly mentions that the earthing of lightning protection system can be interlinked with power system and this telecommunication systems. So many people will tell that lightning protection earthing should not be interlinked with power system earthing and telecommunication system earthing. But standard clearly mentions that single integrated earth emission system is preferable for this lightning protection system. They have clearly mentioned that lightning protection system, power system earthing and telecommunication system earthing can be bonded below the ground level to achieve this single integrated earthing system. So this is the reference from IS 732. So in IS 732 also they have clearly mentioned that interconnection of earthing system is preferred. So here they have mentioned down conductor for lightning protection system, and this is for protective and functional earthing system. So all these earthing are interconnected. So they have clearly shown in image that separate earthing is not preferable, and we have to go for this interconnected earthing system. So this is the reference from standard 62305 and IS 732. So isolated lightning protection system. So this isolated lightning protection system is commonly used for explosive storage areas. So if we are storing some explosives where we cannot place this air terminal or down conductor on the structure to be protected itself, then in that particular case we will be placing these components at a distance at some distance away from this building to be protected. So that is commonly called as isolated lighting protection system. So in this we can find that this air terminal, down conductor and air all are provided separated from this structure to be protected by some distance called separation distance S. So here also we can find that this is no way that air emission system and down conductor system is not having direct electrical contact with the structure to be protected. So this is commonly used for explosive storage areas and oil and natural gas storage areas. So installation. So the installation of this lighting protection system plays a very crucial role regarding the performance and protection of the structure. So there has to be a proper coordination between the designing and this installation. So it is not recommended to install this down conductor along this pipelines or gutters because the corrosion effect will be much higher. So we have to clamp the down conductors at a maximum of 1 meter. So maximum distance between the two clampings can be maximum 1 meter. And it is always recommended to clamp this down conductor near the corners. And if there are any metallic structures, then we have to go for this equipotential bonding. And usually the test links will be provided at a height of 1.5 meters from the ground level, and the conductor should be laid below the ground level at a depth of 0.5 meters, which is 500 mm. The conductor, if we are using for this down conductor or any earthing conductor, means we should maintain minimum of 500 mm from below the ground level. It is not recommended to lay the conductor on the surface itself, because during this risk assessment we have explained about this step and touch potential effects. So it is always recommended to lay the conductor below the 500 mm from the surface level. And we have to go for this equipotential bonding, which involves bonding all the metallic structures near this down conductor to the same earthing grid. So equipotential bonding should be done, and the conductor should be laid below the ground level at the depth of 0.5 meter. And the purpose of test link is, if this earth pit or earthing is not accessible, then we can disconnect the link to this down conductor and we can measure the earth electrode resistance at the test link point itself. And for checking the continuity between these two test links, then we can use for this test link. For example, if you take this as an example, and if there are so many down conductors taking in one system, then if I disconnect this test link from the ground, and if I found this continuity between these two test links, then the path will be closed through this down conductor only. So for inspecting the condition of this down conductor, that is continuity of the down conductor, this test link can be used. while inspecting the earthing, I will be disconnecting the connection from the down conductor and I will be checking the condition of earth beds. And for checking the continuity between the test links, I can disconnect the continuity through the earth beds and I can check the continuity between the two test links for verifying the continuity between the two test links. So these are some of the parameters that has to be considered while installing this down conductor. And one more thing is, while taking this down conductors, any power line or data line should not run in parallel to this down conductors, because during lightning conditions, if any lightning current flows, then there will be electromagnetic induction will be there. So we have explained about 4 sources of damages. So the fourth source is lightning striking near the power line or data line. So if lightning strikes on this air terminal and if this current is flowing through this down conductor, then definitely there will be magnetic field surrounding this conductor. So if any power line or data line runs parallel to this down conductor, then because of this field, there will be some surges induced on the power line or data line. So we need to maintain some distance between this power line and data line from this down conductor. So this down conductor should not be laid along with this power line or data line. So that has to be kept in mind while laying this down conductor system. So maintenance of LPS. So as I mentioned, maintenance should be done properly to ensure the proper operating condition of this lightning protection system. So all the components are exposed to the atmosphere. So periodical inspection should be done to ensure the operating condition of this lightning protection system components. So the first thing is to check the condition of this air terminal. So the air terminal is the point which intercepts the lightning. So whether the air terminal got damaged while intercepting any lightning or not. So whether it is in good condition, and what is the effect of corrosion on the air terminal. So during every AMC, we have to clean the air terminal and we have to disconnect the air terminal from the place. We have to clean it and we have to reconnect the air terminal, and we need to ensure proper connection between this air terminal and the down conductor. So in this conventional method, we are simply providing a bypass to the lightning impulse current by providing an alternate path to the ground. So here we are providing an alternate path so that the current won't enter into the building to be protected. So the continuity plays the most crucial role. So we have to ensure proper continuity in the air terminal, and we have to ensure the continuity between the air terminal to the earth point. That is, there should not be any breaks or loose connections in the down conductor as well. So if we are using this aluminum rod, the aluminum rod or cable can come in 100-meter rolls. But if you are going for GI strips as down conductor, the GI strip length can be only 5 meter or 6 meter. So after 5 meter or 6 meter, there will be one joint. So over a period of time, the chances for loose collection will be very much higher. So we have to inspect the condition of all the fasteners in the down conductor system, whether the joints are proper, whether is there any loose connection in the conductors, whether there are any marks of corrosion on this bolt and nuts and the screws. We are clamping this down conductor on the wall or the structure to be protected. So the screws must be in the good condition. If because of the corrosion, if any screw got damaged, it cannot withstand this wind pressure. So the damage in one clamp may result in continuous damage of the remaining clamps as well. So we have to ensure the good condition of this all the fasteners, and the continuity plays a crucial role. So we have to check the continuity between this air terminal to the earthing as well. So this is why physical damages in the down conductor, and this continuity can be checked using this test link also. And if we are providing any counter, means we have to inspect the counter condition, whether there will be any increase in the count after lightning. So during periodical inspection, we have to maintain a report, like what is the reading in the counter. So after the AMC, that is after the maintenance, between this next AMC, is there any lightning strikes recorded on the counter? We have to note that value also. And regarding this earthing, the proper termination connection should be ensured. So there should not be any loose connection in the earthing system. All the connections should be checked properly, and we should disconnect and we should reconnect it properly. And since it is outdoor application, it is always recommended to go for this SS bolt and nuts than the GI bolt and nuts, because the corrosion rate in GI will be little higher. So it is always recommended to go for this SS bolt and nuts, because if there occurs any loose connection in this down conductor element, it will be very difficult to do the reworks and all. So it is always recommended to use SS bolt and nuts in this outdoor applications. And the earth electrode resistance values, standard specifies that the termination system value should be less than 10 ohms. So they have not mentioned that the earth electrode resistance is less than 10 ohms. They have clearly mentioned that the earth termination system value should be less than 10 ohms. So here they have mentioned. So they have mentioned about the no, it is not the value of only one earth electrode, it is the combined resistance value. So the combined resistance value should be less than 10 ohms. So here they have mentioned earth termination system. So it is not the value of only one earth electrode, this is the combination of all the earth termination systems. So we need to measure the value of earth electrode resistance as well. So conclusion. So if we are providing this lightning protection system, it is a combination of both external as well as the internal lightning protection system. So by providing this external lightning protection system alone, I am not providing protection to the electronic equipments housed inside the building. By providing external lightning protection system, I am providing protection to this building and structures alone. I am not providing protection to these electronic equipments housed inside the building. So physical damages alone can be protected, and if any surges comes from outside the building, the electronic equipments inside the structure are not protected from the surges coming outside this building. And to determine the proper suitable level of protection for that particular site, proper risk assessment should be done properly. So after this proper risk assessment only we can go for this suitable level of protection. We cannot go for this random level of protection, like for residential building I need to go for level 4 protection. So I cannot go for this random level of protection. I need to perform proper risk assessment, and after that risk assessment only I can go for this particular designing. And simply placing an air terminal at the center of the building and connecting to the ground won't solve the purpose. So it involves proper designing. We need to perform proper designing as per the suitable positioning methodologies, either by protection angle method or rolling sphere or mesh method. We need to determine number of air terminals required for the particular site and position of this each air terminal. So there has to be a proper coordination between this designing as well as the installation. So if the designing person is positioning this air terminal at one point, then the installation also should be done as per the design. There should not be any changes in the designing. So if there are any changes, then it will have a huge impact on the protection of the building. So if we execute the design, then only we can claim that the structure is completely protected against the lightning. So we need to ensure that the designing is execution is done as per the designing only. And if there is a small building and we are providing only one air terminal, then the minimum number of down conductors should be 2. The minimum number of down conductors should not be less than 2 numbers. And if I am going for type A earthing, the number of earth electrodes in one lightning protection system shall not be less than 2 numbers. If in any case the number of earth electrodes should be 2 numbers, and periodical maintenance should be done properly. And if we go for this installation for this high-rise building, there is one more difficulty due to the side flashes. So during this first slides I have explained about this 3 types of lightning. The third type is cloud to ground lightning, but apart from that intercloud and intra-cloud lightning is also there. If the height of the building is much higher, then the building will be entering into the cloud zone. So in that case the lightning traveling in the cloud may also have an impact on the buildings. So that is called as side flashing. So if you take the buildings of height above the more than 60 meters, so in that case the probability of lightning striking the side of the building than the top of the building will be little higher. So we need to provide additional protection measures for the building which are greater than 60 meters. So we are planning to organize one more webinar which will be mainly concentrating on this risk due to this lightning on high-rise buildings. So we will explain this designing parameters specific to this high-rise buildings on that particular session.